Hello everyone, welcome back to the EC475 HFSS tutorial. In this tutorial, we will introduce the HFSS Optimetrics, like we will see how to parametric sweep, do the optimization, have a sensitivity analysis, statistical tuning, and we will see the pre-solved example, the shorted prop-fed patch antenna, and we will see the effect of the uh, feeding position of antenna uh, analysis and like input impedance or as parameters. After we will move to HFSS and see how to design the dipole antenna. Now let's move on to introducing the HFSS Optimetrics. Optimization is a process to finding the better or the best design solution or suitable one among the possible design variation. There are lots of variation and design parameters that optimization helps us to find out the better or the best one in our design. Optimetric is an add-on module which gives us some analysis tools like parametric sweep analysis, optimization, sensitivity analysis, statistical or tuning one. This analysis module is compatible with all ends of 3D product like HFSS and allow us to have a full analysis for multiple variables. This features Optimetrics allows us to define model parameters and to have an automate parametric sweep or perform a real-time parametric tuning by using analytical derivatives, or we can identify the performance specification to optimize. You can choose a cost function and the goal function and whatever you want in the optimization process. Or you can also perform a sensitivity and a statistical analysis on optimized model. For doing the optimization, the process is the first you need to create a parameterized model. You can after that you can define a design parameter to vary like model geometric like size, shape, orientation or quantity, or material properties like lossless material. You can define a parametric complex media and isotropic media like that, or some metamaterials. Also, you can define parametric boundaries like impedance or conductance boundaries and so on. Also, you can define a parametric solution setup or solution type. After you define or parameterize the model, the optimization can be performed through a cost function, and you can optimize the circuit parameters like S parameters, Z parameters, or Y parameters. Also, you can do the optimization on antenna patterns like directivity, gain, axial ratio, and like emissions, and some feed quantities like radiation power and so on. For parameterizing the model, you need to go to the parameters window, and you can define a positioning, parameterize the position of the structures, the X size or Y size or Z size, and whatever. These variables can be easily entered. These parameters can go to the local variable, or you can define it in a global one like a project variables, and it can be included units, or you can define the units in the parameters windows. For parametric analysis or parametric sweep, first you should create a nominal design with variables which is associated or assigned to the model aspect which wanted to change. First we define one or more variables which wanted to sweep. For example, in this downside picture, you can see the variable is width and length, and the sweep is defined as a linear step from 12 millimeter to 17 millimeters with the step of 2.5 millimeters. And for the length, is a linear sweep from 8 millimeter to 12 millimeter with a 2 millimeter step. You can define the number of variation or number of steps or the step size, whatever. We will see how to define it. In this feature of the HFSS is mostly used because these procedures help us to determine the reasonable range of the variable values, or you can see how the change of the result by sweeping the one parameters or two parameters, and this way you have the figures. By this way you have the background to see how the parameters change and effect of this changing in the parameters or variables to the especially to the result of the antenna, like S11, the radiation pattern. If you change the width or length of the antenna, how would be the change associated with the radiation pattern or with the S parameter or input impedance. Another feature of the HFSS is the optimization analysis. In optimization, you should define a cost function and optimization goal. As I said before, the cost function can be field values, S parameters, ID mode data, and or whatever, Z parameter, Y parameter, and you can define the goal like you can see in the figure. The calculation is for the reflect, and the frequency for a single value at 8 GHz is the goal is the condition is going to the equal or smaller than our goal. And optimetrics changes and the iteration process will take place to changes the design parameters value to meet the goal. And also you can define the acceptable cost or acceptable error or the noise you want to see in your result. For doing the optimization, there are several analysis parameters should be defined and should be specified, like a cost function. The optimization process goes to minimize the cost function, so you need to define the cost function. For example, the S21 is equal or larger than 1, or you can define the cost function to be a magnitude of the S11 or in the absolute value of the S11 or dB, whatever you want, whatever the HFSS allows us to define. You can express the cost function. Acceptable cost is the value of the cost function at which the optimization process stops. It may be a positive or it might be the negative. You can define it. Also, you can define the goal weight. If you have a several cost function, you can order it or prioritize it. or you can define the step size of the optimization process. If there are several algorithms, we will go back on it, and you can, the algorithm limits the minimum or and maximum of the individual optimization variables that you can define. So you can define a step size, you can define the variable maximum and minimum, the limitation of the variable, and also you can define a cost function noise, which is for EM field is a numerical calculations, which is introduced various source of noise to cost function and change the finite element mesh. These are the several analysis parameters that should be specified to run the optimization in HFSS. So you need to know about each of these parameters and also define it in your optimization window, and then you can run the optimization and see the result if it's satisfy your design or not. These are the HFSS optimization algorithm, Gaussian-Newton, sequential nonlinear programming, SNLP, sequential mixed integer nonlinear programming, pattern search, which is the gradient fair optimization, or you can use the genetic algorithm. The Gaussian-Newton algorithm types are uses the gradient approximation of a cost function and to search a minimum location of your cost function, and it's all of them it's iterative methods. For the Gaussian-Newton, this method using the second order derivatives to accelerate the convergence. This Gaussian-Newton method is are typically using if you are a good initial value of the optimization, and then by the Gaussian-Newton optimization algorithm you can go to the optimum value of your design. So if you have the initial guess and it's really good, and this algorithm help you to find the best answer of your design. Sequential nonlinear programming also is like a Newton optimizer, but it assumes the optimization variables are continuous. Also sequential mixed integer nonlinear programming that can be deal with the discrete integer variables as well as the continuous variables. If you have a two kind of variable, it's good, but all of them are Newton based optimizer, and you need to have a good initial guess of your design. Also, another optimization algorithm is a gradient based or is a pattern search or the genetic algorithm. All of them are iterative processes. The pattern search is if you don't know, if you are not have a good initial values, if you don't guess the initial values of your design and you want to optimize your design, I think the pattern search would be the best option for you to optimize your design. As you can see, it's preferred when the numerical noise is significant and you don't know where you are in the process of the optimization. And genetic algorithm is the popular algorithm optimization process. You need to define a number of generation to get the best overall result. These are the optimization algorithm of HFSS. If you as I'm experienced, if you have a good initial value, it's good enough to have a Gaussian-Newton based optimizations. But if you don't know where you are, if you don't have any initial guess, the pattern search algorithm would be good to achieve your best result. Another feature of the HFSS is a sensitivity analysis. It's used to determine the design sensitivity to small variations in specific parameters around the specific design point. It can tolerance a design to ensure a design goal, and for example, you can determine the maximum or minimum acceptable deviation for substrate permittivity of a macro-strip line to ensure the impedance is well matched. So now let's move on to see the shorted prop feed patch antenna with Optimetrics analysis. In this analysis, in this example, we're gonna to see how to create a variable on the set of a parametric study of a prop feed patch antenna by using the HFSS. This parametric sweep will be defined to see the effect of the input impedance of the antenna, and to see how the position of the feed can be used to match the impedance of the antenna, and it be a function of the feed pin position. And also this feed position can be used in optimization process to find the optimum position of the feed. Also, we can run the analytical derivatives to use how the sensitivity of the design for the position of the profit of this patch antenna. So we're gonna use one of the HFSS example, which is the shorted profit patch antenna, and we can set the setting tools options, and then as we know, he has we define, or the HFSS example has been defined the feed position as a variable that you can see in the properties manager properties windows, which the value is 11 millimeters. And by going to the HFSS toolbar and selecting design properties, you can see the properties windows, and the feed position is defined the value of the 11 millimeters. You can analyze the sweep parameters of this profit position, and can have a parametric sweep of this feed position. This feed position is defined a variable to vary the coaxial feed position in order to achieve the optimal match between the patch antenna and the coaxial feed line. And the ratio of the coaxial feed inner and outer diameters are chosen to achieve a 50 ohm characteristic impedance. And so we will effectively we can change the value of the feed offset until we get our desired desired position, desired result, which present a 50 ohm load impedance of the coaxial feed line. The S11 with the frequency plot can show us where is the resonance frequency of this patch, and the dip is maximized when the optimal offset is found. So in order to create a parametric sweep, we gonna to HFSS toolbar and select the optimetric analysis and select the add parametrics. Under the variable check feed position, we can select it and select the linear step from start 7 mm to 13 mm by a step size of a 2 mm. Then click add, and we can go into the project tree and using in the optimetrics window, using the parametric setup one, and right click on it and select to analyze. We will go back then in the HFSS environment and see how this works. We just now to introduce how to create a parametric sweep. And after running the HFSS, we can go to the result windows and choose the rectangular plot and set the solution to setup 1 sweep 1 and set the domain to sweep, and going to the trace tab, select the S parameter categories and quantity S11, and we can see the S11 as a function of the dB, and we're gonna to families tab and ensure all under values of the variable feed position are selected, and then we can click on the new reports. As you can see, here is the S11 reports by varying the feed position. The red one is going to feed position of 7 mm. As you know, I think the blue one is the best feed position of this step, and 11 mm is a good position that our patch antenna can be matched with our 50 ohm coaxial line. Also, we can doing the optimization for this simple example, and for simple design we have only a single variable, and we can use the optimization and target a minimum. We can create a goal or target to get a minimum S11 less than a minus 20 dB at 1.8 gigahertz and see the result. For create an optimization setup, we need to go to the HFSS and select the design properties. Under the optimization tab, we need to check the feed position variable and set the minimum and maximum value to optimize in this limit, and then select on OK and run the optimization. And then define the optimization setup. Going to the optimization setup, HFSS optimetric analysis, and then select the add optimization. In the optimization setup, you need to click on the goals tab because the initial value is closer to the desired one. We need to just click have a Gauss-Newton algorithm with the maximum number iteration of 10, and click on the setup calculation button, and also you can define a goal with report type of model solution data with this in a solution tab click on the setup 1, sweep 1, category as parameter, quantity S11 in the DB function, and click add calculation and click on the down button. You can see in the windows that the calc range is in single frequency 1.8 frequency. The condition is equal and smaller than, the goal is minus 20 dB and weight is 1, and acceptable cost we can define it 0 to get our desired one. Also, we can set up the optimization with clicking on the General tab or Parametric Analysis, Parametric Setup 1, and doing the optimization. After running the optimization, you can see the optimization result by going to HFSS Optimetric Analyzer and see the Optimetrics result. As you can see, the optimum value solution occurs at about 10.5 millimeter. Here you can see the optimum value result by going to the HFSS result tab and select on the rectangular plot. Solution setup 1, sweep 1, domain sweep, and category as parameter S11 in DB, and families tab you can select the value which is your desired goal in optimization. But if you didn't check the families tab, it's gonna be the optimum value, and because the optimum value is update the variable. Now let's move on to designing a dipole antenna in HFSS. As you know, dipole antenna consists of two conductors and fit in the middle of this antenna. As you know, the dipole antenna's length with respect to the wavelength, it can be determines the operation frequency and the radiation pattern. So the length of the dipole is critical, and it shows the frequency of the operation and the gain of the antenna. If the dipole is lambda over 2, it has the highest gain, and for the lambda over 4 we can simulate the antenna parameters. So let's move on to see the design steps. First of all, we need to choose the solution type, which is the model analysis. Then design our model with using toolbars. It consists of the two cylinder and the FET between it. Define excitation wave for the LAN port. It's better to excite the dipole antenna with the LAN port elements, like as we define it in a small loop dipole antenna, magnetic dipole antenna. Then we should define boundary conditions, define a solution setup, add a frequency sweep, define an optimetrics to see the best result, and run simulation and view the result as parameters, impedance, fields, and radiation patterns. As I indicated, you need to choose a solution type, go to HFSS and select the solution type and select on a model analysis. Then you should design a model. You should define a cylindrical, two cylindrical. You can define a one cylindrical and duplicate it or move it around one axis to have a two cylinder and two conductor cylinders. And also you can choose the material of the conductor. You can use the PEC perfect electric conductors, and also you can then you should excite this antenna and create a rectangle between the two conductors and assign a citation to this conductor or to this sheet, and define modes, uh, line mode of this LAN port element, and start with a 50 ohm resistance, and then we can, in a post processing, we can change the impedance of the excitation. As a boundary condition, it's better to draw a cylinder which has the quarter the wavelength, a prot from the structure, so it can be Landauer 2, or as indicated in HFSS software, Landauer 4 is enough to assign and then we should assign a boundary condition and radiation. We can assign a boundary condition and radiation of it. Also here we can insert a far field setup, infinite sphere, and define our phi range and theta range from phi range from 0 to 360 degree, and theta range from minus 180 to 180. Then we add a solution setup to our structures at a frequency of 1 GHz with a maximum number of paths 20, and maximum delta is 0.02. And then we can add the optimetrics, add the parametric sweep, linear step, start from 70 millimeter to 80 millimeter, step size 2 millimeter is the length of the conductors, length of the dipole, to see its effect on the operation frequency. And then we can view the result, impedance, input impedance. After running the HFSS, we can create in results tab, we can create a model solution data report and click on the rectangular plot and select the solution type, sweep, domain sweep, primary sweep frequency, and see the real Z11 and imaginary Z11 of the impedance. And we can go to the families tab and see that the length of the antenna is assigned to all of the variables, and see the result. Because the antenna should be matched in this result, we can see the imaginary part of which length is near to 0, and then select these impedances, select this length. So as we can see in this figure, the frequency is about the input frequency, the real input frequency is about the real input impedance in 1 GHz frequency is about 75 ohm. Also, in the post-processing, we can modify the port impedance, and going to the right-click on the excitation and properties, go to the general and change the full port impedance resistance from 50 ohm to 75 ohm, and see the S11, because this S11 is defined for 50 ohm, and because we want to see its match for 75 ohm or not, we define the 75 ohm impedance for our LAN port element, her LAN port excitation, and again, as you can see, it's at 1 gigahertz for the excitation of 75 ohm. You can see the SWAN1 is from -10 or -20 dB. You can see the reflection coefficient or SWAN1 of this antenna. Also, we can see the bandwidths, the -10 bandwidths, -15 dB bandwidth, or -20 dB bandwidths, and also you can see the antenna parameters by right click on the infinite sphere and compute antenna parameters. You can see maximum directivity, maximum peak directivity, peak gain, peak realized gain, radiation power, and radiation efficiency. And radiation efficiency, because we use a PEC, perfect electric conductor, and PEC, it's going up to the 1, it's greater than 1. Also, we can create a radiation pattern and see at the x plane at the phi equal to 0 degree, and see the gain and pattern of the antenna. As you can see, it's a donut shape of the dipole. So it has a donut shape pattern, and you can see the antenna pattern of this dipole. Now let's move on to HFSS and design the antenna. So in HFSS, first we check the solution type, use a model analysis, then going to the HFSS design and draw a cylinder, and define the parameters and the position of this cylinder. 0, 0, gap over 2, which we can define a gap about 3 mm. In the z-axis, the radius will become w over 2. W is about 10 mm. And the height will going to L. L is 75 mm. And the number of segments is 0. So we can see our cylinder. Then we can duplicate this cylinder around the x-axis, or we can around the x-axis 150 and total number 2. Okay. And we can assign material to this. Let's say PEC, perfect adaptive. So we need to define a excitation. Define a sheet. Sorry. We are in a XY plane, so define. We need to in a X plane. In a X. Oh. So it's gonna be minus for x minus w/2 for y here in y, and for z minus gap/2. X size would be w and z size would be gap. Okay, it's gonna be here. And then we can right click on this plane, rectangular plane, going to assign excitation, long port element, 50 ohm. We need to integration line, the new line, see the triangle, and again see the triangle to set the middle to middle of this plane. It is defined for characteristic impedances ZPI, Z-port. We normalize it. We can post-process and change the impedance after we find out the impedance of the dipole, and that's gonna be okay for now. And we have excitation. We need to set the boundary again. Again, we need to use and we need to create a boundary and define it. So center position of our boundary 0 0 minus L minus gap/2 and minus lambda/4. Okay, like which is separated by and lambda, it's gonna be for 1 gigahertz 300 millimeter. Z-axis for the radius of W/2 plus lambda/4. For the height of 2L plus gap and plus lambda/2. Can transparent it to see your dipole antenna well. Also, you should assign a boundary to this radiation. Now we have our radiation boundaries, we have our excitations, we have our models. We need to define analysis. Let's go to that solution. at frequency 1 gigahertz. Maximum number of passes 20, and here we can set the minimum number of passes 3 and the minimum convergence passes 2. Let's go to the advanced to save field at 1 gigahertz and see the impedances from, yeah, that's gonna be okay. And also we can set the optimetrics, add a parametric sweep from the defined variable of L, linear setup from 70 to 80 by the step size of 2 millimeter. Now we can check the simulation, validate it, all of things okay. We can right click on the parametric sweep and analyze it. Before you should save it, you can analyze it. So okay. After finishing the simulation, we're gonna do the result. Right click on result, create a model solution, data report, rectangular part, or you can use the result tab. And let's go into the Z11 and see the imaginary part and real part of the all families of L. So we can here see the result at 1 gigahertz. You can see to 1 gigahertz, yes, at L equal to 70 millimeter, it's near to the 0, and for the real part of the Z11, the red one, it's about 76.5 millimeter, and we can shift it to be 0 for about 5 megahertz. Also we can shift this about 5 megahertz. To see exact 75 impedance of the input impedance. So we can go to the excitation, properties, and in the post-processing, or we can also put in general 70, you can in the post-processing or general equal, say the 75 ohm for our input impedance, and let's have the result S11 of this antenna at specific version. Oh yes, here you can see for L equal to 70 millimeter, you can see all the notch or the dip in a S1 or reflection coefficient of the antenna input impedance. It's matched to 75 millimeter, and also you can add the marker to see the bandwidth of a 20 dB, or you can add delta marker to see exact value of the bandwidth of the minus 20 dB or minus 10 dB. Minus 10 dB is okay, and it's about 200 megahertz bandwidth. That this type of antenna has about a 200 megahertz bandwidth. Or I should insert a far field setup, infinite setup, to see the pattern of the antenna. And also you can go to the result far field report, gain for dB, for which phi for 70 millimeter, and for phi equal to 0, because we need to see an X cut or E plane or H plane of the antenna. The X cut would be the E plane of the antenna. Although for a dipole, E plane and H plane of the antenna are equal together. E plane and so let's see the pattern of antenna. So let's see the pattern of the antenna at phi equal to 0. I should run it again. Okay, I run it again, and you can see the pattern of the antenna. It's a donut shape, and also you can see the 3D pattern of the antenna here. So we can hide the boundary condition, and if we plot a radiation field here, okay, now so you can see the dipole, and again we can go to the result, far field, 3D polar, and amplify. Now I'm gonna do just, yes, it's a 3D. In dB, where is it, dB? Okay, you can see a donut shape. Also, this is a gain plot tree going to our model, and plot field, radiation field, plot tree, and transparency, let's say 8, and the scale is okay. Also you can scale it to 1. You can see the pattern of the antenna against our dipole. It's a donut shape pattern. That's it. That's the end of our tutorial. Have a good week and stay safe. Thank you.